Hi, my name is Devon Callanan. I'm a researcher at the NSF Center for Space, High Performance, and Resilient Computing at the University of Pittsburgh. Today, I'll be talking about accelerating regular expression matching on FPGAs with high-level synthesis. First, I want to discuss the goals, motivations, and challenges for this project. The goals. We want to accelerate packet inspection for high-speed networking. We also want to investigate the performance characteristics of OpenCL on FPGAs. This is motivated because faster link speeds demand faster deep packet inspection. Enterprises often use 10 gig Ethernet connections, and even faster 100 gig Ethernet connections are not out of the realm of possibility. Also, FPGA design tools continue to improve. Benchmarking these tools is a good way to understand how they're changing. This work isn't without challenges, however. Throughput scaling costs grow exponentially with this application, and trade-offs between the complexity and performance of high-level synthesis designs are present in the face of RTL development. Now we can jump into the background. What is regex? Regex describe complex patterns in compact ways. Queries are built using metacharacters, such as those found in the table to the right, grouping symbols, such as parentheses, and regular characters, such as the letter A or the number 9. A short example, shown below, is the word color, with an alternation placed on the U, using that question mark 0 or 1 metacharacter. This matches both the American and British spellings of the words color, which could be useful in a mixed corpus, which includes texts from both countries. Regex are used in network intrusion detection, genomics, and natural language processing. What is network intrusion detection? A network intrusion detection system, or NIDS, watches network traffic for suspicious packets. And how do we know these packets are suspicious? Well, security professionals write rules defining which packets should set off alerts in the system. Alerts can consist of packet logging, notification to system administrators, or completely blocking some traffic from entering the network. Each rule can specify a regex as a detection option. The common network intrusion detection system SNORT is an open source system with thousands of rules containing regular expressions. In this work, we use regular expressions from SNORT to simulate a real-world application. What's an NFA? Non-deterministic finite automata, or NFAs, from here on out, are state machines. The image shown below, with the circles and arrows in between, represents an NFA, where each circle is a state and each arrow is a transition between states. NFAs can be constructed to reach an accepting state only after certain inputs. The input patterns, also known as a regular language, described by an NFA, can also be described by an equivalent regular expression. Here we show a regular expression in bold and the equivalent NFA, which accepts the same input character patterns as the regex there. Now, NFAs are particularly interesting for FPGA acceleration because many states can be active simultaneously. This means that they're abundant with parallelization, as many transition criteria must be checked at the same time. Also, NFAs are amenable to hardware acceleration because they're made of simple hardware constructs, such as states and combinational logic. Now we'll take a closer look at an NFA search algorithm, as it's pretty integral to the following work. As you can see, here's the same NFA representing the regex on the previous page. The input text shown at the bottom here starts with a capital B, which transitions activating these initial states here, now in red. The next input character E will match the criteria of only these two transitions, and they can be checked in parallel on an FPGA, resulting in the next two active states. Another E, however, only activates the transition from state 6 to state 7, and we follow with a T and an S, finally activating the accepting state here. We know that we've found an input character pattern which matches both the regex and the NFA. Now we can take a look at high-level synthesis. So we know traditional FPGA development is used to describe hardware constructs and often uses fine-tune optimizations to make things work as efficiently as possible. This is known as register transfer level, or RTL programming. VHDL and Verilog are common examples. High-level synthesis, on the other hand, abstracts some fine-grained optimizations to ease development and allow rapid prototyping. Often in the form of C or a C++ compliant language, this allows FPGA developers to describe logically or functionally what the accelerator should do, rather than describing the hardware under the hood. Intel provides access to HLS through OpenCL and oneAPI, both of which are specifications developed from the Kernels group. oneAPI obviously is based on top of SYCL and provides additional extensions. So, putting these all together, we're accelerating regular expression matching on FPGAs with high-level synthesis. We want to handle enterprise-level data at enterprise-level speeds. We want to do this using regex from the popular network intrusion detection system SNORT. And we want to do this by transforming these regex into state machines for easy parallelization. We're then putting these into hardware on FPGAs. And finally, all of this is done using high-level synthesis. Let's now take some time to look closely at the kernels which are realized using this HLS approach. As we said, HLS allows for C-like coding of accelerators. Representing NFAs, which are state machines, requires just a set of states and transitions between those states. As we know, states are either active or inactive, which allows us to store them in local memory on the FPGA as simple Boolean arrays. Transitions are combinational logic, which combine the input character, the active set of states, and the criteria for each transition to form a future next set of states. These can be realized using if-else statements. As you can see, the kernel, shown on the right, is fairly simple and only consists of 4 states. These states are realized using a current array and a next array. For each input character in the input stream, the transitions decide which states will be active next based on the input character and the current active states. Those next active states are then transferred into the current active states, and the process is repeated for the following input character. Although this kernel is fairly short and under 30 lines of code, most real-world regular expressions generate NFAs that are hundreds of states and contain even more transitions. We also want to realize as many of these regular expressions on an FPGA as possible, leading to source files that are often tens of thousands of lines long. To combat this, we use automatic source generation, where we take the representation of the NFA and simply pass it into a template, where then the OpenCL source is generated. The OpenCL kernels are compiled and launched as single work item kernels, which is the recommended mode for FPGA development. The accelerator is also fed by an inferred burst coalesced load store unit. This loads multiple sequential addresses so as to hide long DDR access latencies for the input text. Looking at some initial performance from the compiler, we can see that the initiation interval of the main NFA computation loop is 1. This means that on every clock cycle, a new input character is read in and fed through the parallel transitions of the NFA. We can see that the compiler achieves a maximum operating frequency of around 293 megahertz, and the kernel achieves 2.3 gigabits per second of throughput, using about 100,000 lookup tables. We can also infer from the reports that shift registers are used for simple repetition schemes on the OpenCL compiler. Before we continue with any further discussion of results, let's take a step back and reconsider the goals and motivations of this project. We wanted to perform accelerated regular expression searching on enterprise-grade networks. This means we wanted to reach at least 10 gigabits per second of throughput, and potentially much more than that. However, as we just saw, we reached about 2.3 gigabits per second, not even close to our initial goal. As such, we explored methods for increasing the throughput. Namely, we looked at scaling the input bandwidth. The input bandwidth of an NFA can be increased by transforming the number of input characters that each transition takes. The transitions in and out of each state are concatenated together to double the input bandwidth in such a transformation. We'll now take a look at this NFA here and how input character transformations can create a 2-character matching NFA, allowing you to double the speed of the design. Here, in state 0, we look at all transitions into and out of the state. We then concatenate these transitions together, forming one large transition, which checks the criteria of both smaller transitions. We can do this on each state, even more complicated states with multiple input and output characters. Here, we see state 7 has an input transition with the criteria N and one in red here with the criteria I. First, we start with the criteria N transition and concatenate to both green output transitions. We then do the same with the input I transition. As we can see, this creates a number of new transitions, but allows us to effectively skip states in between or read more input characters in than we previously would have on each clock cycle. With this complete, we can hopscotch through the NFA at twice the speed we were able to before, effectively doubling the throughput. Such a transformation isn't without cost, however. As you can see here, as we double the number of input characters, we get an exponential explosion in the number of transitions marked in blue on the graph, despite the number of states remaining constant. To get a better visual representation of how and why this is happening, we'll look at a couple simple NFAs and how they react to transformations like the ones we described on the previous slide. Here, a very simple single character matching input NFA. After a transformation, each transition now matches 2 input characters as criteria, and we can jump through at twice the speed. However, the complexity has increased. Doubling again increases our throughput. However, complexity is beginning to explode here. And this is with a very simple NFA with very few states. If we look at a real-world NFA from the snort intrusion detection system, we can see that this is even more of an issue. Here, we are matching 4 input characters per transition and have tens of states as opposed to the 9 states on the previous NFA. As you can see, the complexity here will likely add to the resource utilization and the complexity of the place and route system for the FPGA. With that in mind, we can now take a look at some of the results. The results were collected on an ARIA-10 programmable acceleration card using the OpenCL SDK version 19.4. The ARIA-10 has about 800,000 lookup tables in this iteration and is manufactured using a 20 nanometer node. First, we can take a look at the maximum kernel frequency for each of the kernels. As you can see, the Intel offline compiler for FPGAs using OpenCL is able to realize a fairly consistent clock frequency despite the added complexity that comes from increasing the input bandwidth, as you can see along the bottom here. We barely dip below 300 megahertz and remain fairly constant there. As a result, since we mentioned that the initiation interval of this kernel was 1, we can directly relate the clock frequency to the throughput of the design. Here we can see that as the clock frequency remains stable, despite doubling the number of input characters read on each cycle, we can effectively double the throughput of the design through these transformations, reaching 17.9 gigabits per second, which is well above our original 10 gigabits per second goal. We do, however, notice the added complexity of the input bandwidth scaling when we look at the lookup table usage of these designs. As you can see, the first 3 input bandwidth scaling kernels, 1, 2, and 4, have fairly even lookup table usage. However, this jumps as a part of exponential growth when we scale again to the 8 input character kernel. This is likely due to the added transitions and complexity of routing the design on the FPGA. With these individual results in mind, let's take a step back and look at some prior arts and look at how they compare for the actual application of network intrusion detection. We know first that we want high throughput designs, and we can see that our design is best in class here with 17.88 gigabits per second maximum throughput, far outstripping those of the prior works, even those done in RTL. Now, this is not the entire story, as system administrators would like to implement as many regular expressions as possible and as many rules from the network intrusion detection system. This requires efficient use of onboard resources. As such, we introduce another additional metric used often in the prior arts. This is throughput efficiency, which normalizes the throughput by the number of lookup tables per state used in the design. This helps create a level playing field between designs that use different NFAs in their work, and also shows how good the design is at efficiently utilizing resources. As you can see, the RTL work done here by Yang and Prasanna reaches a 10.1 throughput efficiency, while our work is only at 1.43. This is due to the fact that we use almost 10 times as many lookup tables per state as the optimized RTL found in Yang and Prasanna. Both Yamagaki and the Clark work use RTL as well and have efficient, low lookup tables per state, however lack in throughput. Looking now at our conclusions and future work. We've seen that our throughput scaling for HLS kernels is fairly good. However, it's unsustainable past the 8-character bandwidth, as transition explosion becomes exponential. Comparing to prior RTL solutions, we see that our throughput is best in class among similar work. However, we do the worst in terms of resource usage efficiency. In terms of throughput efficiency, we're near the bottom, however, still competitive with some of the prior RTL work. For future work, how do we scale past 20 gigabits per second as network traffic is increasing all the time? We can do this through data pre-filtering. We know that most traffic is not malicious, and if we can accurately and quickly filter out many of these non-nefarious packets, we can provide regex searching only on those most suspicious packets. If only 5% of the packets are suspicious, we can then only slow down the pipeline for those 5% of the packets that need full verification by the NFA. Thanks for taking your time to listen to this talk. I'd like to thank all my coworkers back at the SYCLcon lab for their support, and also NSF for the grant and the industry members that support this work. Thanks again.